Hello everyone, welcome to this video. In this video, let's move on to our next question, which says here, suppose F1 and F2, they are distinct reflections in a dihedral group Dn such that F1 F2 is equals to F2 F1, right? So we need to prove that F1 F2 is equals to R 180 degree, right? So this is what we have. Now in any dihedral group, we denote it by Dn. This thing we all know. And the order here for the group Dn is 2n, so that means it would have n reflections and n rotations. This thing also we know previously, right? So if we denote all the n reflections by f of k, f subscript k, and all the rotations by r subscript 360 by n, right, where n is how many times you are rotating it. So here, suppose because in the question we are given F1 and F2 as distinct reflections such that this thing is there, so we assume this thing and we call this by equation 1. Moreover, we know any in the dihedral group, any reflection followed by any reflection gives you a rotation. This thing we have covered in the previous question, right? And you can go there and see the result. So we had named it by the analogy of odd and even. If this is odd, then odd and odd becomes even. So this becomes rotation, correct? And moreover, in the previous video, I told you that a reflection followed by a reflection gives you identity. So that means the reflection is the inverse of itself, right? This thing also we know. So let's mark this as our equation 2, and thereafter, if that is there, so because there are so many reflections and so many rotations, so we fix the index I. For this index I, our rotation Ri would be equal to what? It would be equal to, say, for some fixed I, it would be equal to F2 and F1, which are given to us in the question, correct? These two reflections. So let's mark this as equation 3. Now, using this equation, we can now write this quantity F1 F2 F2 F1 as, you can revert it, right, using equation 1 because this thing is given to us here. So F1 F2 is F2 F1 and this thing is same. Now using 3, what do we have? We have the value of F2 F1 as Ri, right? So keeping it here, and the value of F2 F1 as Ri, so keeping it here, it would become Ri square. So let's mark this as equation 4. Correct? And now using equation 2 and equation 3, we can again write this term as F1 F2 F2 F1 as, you can use associativity first, right? Now what is reflection followed by reflection? As I have told you here, it is a rotation, which is the identity rotation. So it is a rotation here. Now when you compose any element, any reflection with a identity element, it is again F1, right? What is F1 F1? Again using the same, any reflection followed by itself gives you the original position back. So it would give you the identity rotation, which is you are doing nothing to it. So that means from here we obtain this as equals to R0. So when you compare your equation, this 4 and equation 5 from here and from here, you can see this Ri square is equals to R0, correct? So this Ri square is equals to R0, and what is R0? It is the identity element. So in Dn, if you remember, we only have this identity element, the square of some element is equals to the identity element is only there when we have the rotation by 0 degree. That means we are not doing anything. Identity square is equals to identity, and it is by 180 degree, because once you apply 180, whatever is your object, it would rotate 180 degree, and thereafter once you applied 180 again, it will come back to the original position. So it is again R180. Hence your Ri becomes equals to R0 or R180, correct? So these are the only two possibilities present with you, but your Ri in this case cannot be equal to R0. Why? Because if it is equal to R0, then your F1 and F2, they would become equal. Why? Because in that case f1 f2 would be equal to r0 and f1 would become equal to f2, because this is only possible when you have the same reflections, as we have seen in the previous question. So using this fact here, your f1 f2 is equals to r of 180, and this is what we wanted to prove here. So I hope you understood this question well. Well, that is it for this video. Thank you for watching.